Good afternoon. Good afternoon, everyone. I'm really happy to meet all of you here. I'm sure we'll meet soon in Israel and we'll have amazing competition. But to start off the competition, we have invited Professor Lior Elbaz to give us an overview about green hydrogen. He will introduce the subject to you. And I know a lot of you have questions. So Lior, please let's leave a few minutes for a Q&A afterwards, okay?
You'll need to stop me in the middle because I like to talk. So.
Okay. So yeah. So everyone, I'm going to ask you to put on mute and Lior will turn on his camera.
Okay. Just a second. I'm not on. Just a minute. Okay.
Lior, hi Lior. צהריים טובים, good afternoon. The stage is yours.
Okay.
Yeah, he's co-host. Yeah. Avivit, תעשי אותו co-host.
Okay. Just a second.
That's fine.
You can share. It's okay.
Share.
Okay. So Lior, thank you. I'm going to thank you in advance, and the stage is yours.
Okay, so everyone sees my presentation on their screen?
Yeah, we can see it.
Good. So welcome everyone. I'm happy to join this initiative and support Eilat a lot in the transition to green hydrogen. And today I'm going to give you a talk about the whole scheme of things, how things are working, why do we need green hydrogen, or why hydrogen economy is going to be the next thing. I'm going to explain very briefly how things are working, and we leave the specifics to the question. So I'm sure that many of you have already read about hydrogen and fuel cells, and we will serve the specifics to the questions. Okay, so we'll start off with the motivation. So we all know that we've seen the climate change. We are seeing that the temperatures in the world are increasing, and I could say that for me, I'm 45 years old now, but as a child, I remember that in Israel we have four distinct seasons. We had the summer, spring, fall, and winter. But today we basically have just one season, and this is due to climate change. This is a movie. Just a second. This is a movie that was released by the UN. I'll let you watch it, and we'll continue afterwards. Please turn on your speakers if they are not on. Okay.
I think you should share the sound.
Not sharing the sound?
No, we're not hearing it.
There's some noise from Edward.
How long is it?
Okay. Just looking. So you can't hear my sound?
We're hearing you, but not the movie.
How do I share the sound? That's a question.
You should go to
share sound. Okay.
Okay.
Can you hear it?
Now hearing it.
Children will be the worst hit by climate change, despite this view that
we fool ourselves if we think we can fool nature, because nature always strikes back.
The eyes of all future generations are upon you, and if you choose to fail us, I say we will never forgive you.
So things are changing, and world leaders are understand this. and they decided to start working together in order to fight climate change. This started in 2015 when the major industrial countries in the world signed an agreement to try to fight global warming and climate change. And they also hired groups of scientists to study if this climate change is man-made or not. And after a long study compiled from 14,000 studies, research studies on climate change, 230 scientists from 65 countries, they came to a conclusion that we are contributing quite a bit to climate change, and we need to change the way we use and make energy. We have to do this in order to basically keep the climate or the warming below 1.5 degrees C. Otherwise, if we go to 2 degrees C, then our lives are going to change dramatically. So everything that we know, from the water supplies to food, to the way we live, to the clothes that we wear, to the air that we breathe, everything is going to change. We need to try to fight it. And I can tell you that we haven't done a good job at it so far. So since 2015, since we signed this agreement, we haven't reached the goals that we committed to. And the situation is only getting worse on a daily basis. So we have to make significant change now and ramp up our efforts. If this is not enough, then let's look at what happened last year around the globe. So to the top left, you could see floodings in Germany. At the bottom, you could see major fires in Greece. We could see to the top right drought in the US. The US has been suffering from a consecutive 23 years of drought. Okay, so I mean, if you look at the most populated state in the US, California, they have no fresh water anymore. Okay, and then on the other side, if you look at China below, major flooding. So the world is reacting to what we do, and not in a nice way. So it's telling us, it's telling us that we need to change the way we behave, and we must do it now. So I'm going to show you a couple of short movies. One from my early, when I was about 30 years ago. There used to be a commercial in the US that actually promoted the production of CO2. This was financed by the oil companies, but that was how people felt in the 90s. So take a look at this.
There's something in these pictures you can't see. It's essential to life. We breathe it out. Plants breathe it in. It comes from animal life, the oceans, the earth, and the fuels we find in it. It's called carbon dioxide, CO2. The fuels that produce CO2 have freed us from a world of back-breaking labor, lighting up our lives, allowing us to create and move the things we need, the people we love. Now, some politicians want to label carbon dioxide a pollutant. Imagine if they succeed. What would our lives be like then? Carbon dioxide. They call it pollution. We call it life.
Okay. So we need to understand that politics is heavily involved in what's happening here. And this is a very good example of how the oil companies were trying to convince us that basically polluting and releasing CO2 is good for us. There is some truth in it, but it's mostly a lie. We need CO2 in order to grow plants and others, but we're making too much of it. It's like, our body needs sugar, but we cannot, eat too much sugar, because then we're gonna become obese and suffer from different illnesses. So there needs to be some sort of a proportion to anything that we use. And this is a good example of how, you know, the reality could be twisted, and we should be aware of it. After that came, so this was during the George Bush, when George Bush was the president, senior George Bush, and then came his son, and his son was suffering. His son had to deal with you know, environmental organizations who said we need to clean up. So he came up and said to his advisors, "Can you provide me with a solution that is never going to work? I don't want to fight pollution. I just want to fight those environmentalists." And they told him, "Listen, hydrogen is never going to work. Put money into fuel cells and hydrogen." And this is what he did. So let's watch this short movie here. If it's going to show, it's not showing. It's stuck. Anyway, so basically he invested quite a bit of funding into hydrogen, and that was the biggest push towards hydrogen economy and hydrogen production. So we must change the way that we produce and use energy. We know that. We know that the climate is changing, and we need to react fast. The good news is that we have enough sustainable energy to support all of our energy needs. We have enough sun and wind, but the problem with the sun and wind is that they are intermittent. What does it mean? The sun is shining when it's shining. I'm jumping through this. The sun is shining when it's shining. This is a graph that shows the energy scheme of California. And you can see here that at 6 a.m. when the sun is shining, they basically make most of their energy from photovoltaics, and then lowering the use of natural gas and other polluting sources. And when the sun is down, they start using again natural gas and polluting sources. We would like to flatten this curve, and the only way to flatten this curve is to find a good solution for energy storage. Now, when we're looking at energy storage, we're looking at energy storage throughout the day. So basically flatten this curve throughout the rest of the days, the rest of the hours of the day. But we also need to flatten the curve throughout the week and months and seasons, because during seasons, if we look at the winter versus the summer, you see that during the winter, we could make much less energy from the sun because we don't get as much sun during the winter. Whereas the summer we get much more, so we need to carry over energy between seasons, and we need to find a good solution for that. So there's been a few solutions that have been studied. The first is basically using potential energy, basically pumping water to the top of the mountain and then releasing them as a sort of a man-made waterfalls to make electricity. This used to be a nice solution, but it's not efficient. It's not efficient because of very different issues. One of which is the pumps are not efficient. Another problem is that the water at the upper reservoirs basically evaporate throughout the day, and if we keep it for seasons, definitely much of the water will basically evaporate. And we're losing all of this media that we wanted to use to make energy. So this solution, this mechanical solution, is one of many other mechanical solutions that are not considered efficient. And that leaves us with chemistry. When we look at chemistry, we look at the periodic table and we look at the elements that we have. And we have hydrogen at the top here, and then below it we have lithium. So those of you who have done some reading, they know that these two elements are very important. Hydrogen is what we're talking about during this lecture that's the topic of this lecture. And then lithium is for batteries. So we could use batteries. They can work, but batteries have serious issues when it comes to energy storage or energy storage in large quantities. And one of the main things is self-discharge. Basically, if you leave a battery for long periods of time, days, weeks, then you try to operate it later, then you found out that it's basically drained. Okay, I'm sure that you've had that occasion when you left for a vacation and then came back and your parents tried to turn on the car and the car didn't start. It didn't start because the battery was drained, because of self-discharge. So batteries are very good for certain applications, but it's not good for large energy storage. And that leaves us with hydrogen. Okay. So I'll come back to this slide later, but I want to jump into hydrogen. Hydrogen could be produced. Hydrogen can be produced from water. Basically, putting two electrodes in water and applying a certain potential between them would basically break the H2O, which is water, into H2 and O2. We can then store the hydrogen that we're producing and then later use it to make energy again. Okay, so this is the basic of hydrogen economy. Basically, this is how we make green hydrogen. The technology that we use to make it is called electrolysis, basically breaking up water. Okay, we break up the H2O into its basic components, H2 and O2. Now, at this point, many ask me about safety, and when they type in hydrogen, they would see that they would see the Hindenburg, and they see that it's going on flames, and they say, "Oh, hydrogen it's not safe." And the answer to that is this figure. This figure shows us basically the holy trinity of fuel safety, and the further we are from the 0 point here, okay, on this graph, the better we are. Okay, and as we can see here in green, hydrogen is the furthest on all three parameters compared to any other fuel that we use, from gasoline, the propane that we use to heat our homes and cook, and methane, which is natural gas. Okay, so when it comes to safety, hydrogen is safer than any other fuel that we're using now. Why is it safer? Because it has a lower flammability limit. It has high buoyancy and diffusivity. Buoyancy and diffusivity tell us how fast our material escape the accident area. And to show you how it works, we'll look at these cars. Okay, so if we look at the car to the left here has a hydrogen tank in it, and the car to the right has a gasoline tank in it. Both cars had their fuel tanks blown up. Now, what you can see here is the hydrogen coming out. Okay, this is the lightest element on Earth, and it just floats over everything. So it's basically shooting up straight to the top, whereas the gasoline in the other car is basically flowing underneath the car and lighting the whole car. What we could see here is that after a minute and a half, the hydrogen was depleted completely from the car, and there is no severe damage to the car, whereas with the gasoline case, the car is completely destroyed. So this is hydrogen safety for you and for anyone who tells you that hydrogen is not safe. It is safer than any other fuel that you're using today. Okay, so this brought up the whole idea of hydrogen economy. And in hydrogen economy, what we're saying is that we're collecting the surplus of energy that we're produced from sustainable sources, mainly wind and sun, and we could use it to break up water into hydrogen and oxygen, and then take it and use it for different applications from different polluting industries, such as the metal refining industry, the fertilizers industry, which uses ammonia, and then transportation. And if we want, we could put it back to the grid, to the electrical grid, and make electricity to be used by industry and domestically. Okay, so this is the idea behind the use of hydrogen. We could use hydrogen as a storage molecule and then use it for a variety of applications. Now, why hydrogen? I mean, economically, why should we use hydrogen? So this figure here shows you why, or gives you the answer to why. If we look at the energy scheme in Germany, which is also relevant to most industrial countries, we see that most of the energy is transported in the form of molecules, not in the form of electrons. Electrons are on the electric grid, whereas molecules are gasoline, natural gas, propane, and whatever molecular fuel we're using. Why does it look like this? Why 80% of the energy that is transported in the form of molecules and not in the form of electrons? The answer to that is because it's cheaper, okay? The infrastructure to build a convection utility for transporting electricity is about 10 times more expensive than the cost of transportation of molecules in pipelines. Okay, so what we see here is a comparison between a high voltage line that goes from the Netherlands to the UK. Okay, the cost of this electric grid line is 230 euros per kilowatt per 100 kilometers. A similar but different way to transport energy here is through a pipeline, which transport natural gas from the Netherlands to the UK again, and the cost here is 11 euros per kilowatt per 100 kilometer. Okay, so 230 versus 11. Okay, the cost of transportation of energy and the infrastructure associated with it is much cheaper when we're dealing with molecules. This is why hydrogen makes sense economically. It's just cheaper to transport it over long distances. And we can see here the comparison. At the bottom, we can see the cost of transporting hydrogen in pipelines over long distances. At the x-axis, you can see the distance, and the y-axis, you can see the cost, whereas transporting it over the grid lines is much more expensive and gets even more expensive as we go to longer lengths. Okay, for this reason, many countries decided to invest in hydrogen infrastructure, and we could see billions and almost $1 trillion being invested in building up hydrogen infrastructure throughout the world. The numbers that you see here are pre-corona numbers. After the corona started, all of these countries decided to ramp up their efforts into making hydrogen a reality. And we're talking again at the $1 trillion investment in hydrogen economy by 2030. The US had also decided to participate in this party and is putting quite a bit of billions of dollars. The numbers here is billions of dollars, quite a bit of billions of dollars in transition to sustainable energy sources, and some of it will go towards hydrogen. Okay, as a consequence of that, these investments, we are seeing now things happening. Today in Europe itself, we have over 160 hydrogen filling stations. We have hydrogen cars, buses, trains. Now we're looking at hydrogen airplanes. We're building hydrogen pipelines now to transport hydrogen throughout Europe, and so on. So we start seeing things happening. And later, when you unmute yourself, I would like to hear if any of you saw a station near their home or saw a car driving in the streets propelled by hydrogen. Okay, so they laid out the hydrogen roadmaps, and many countries, many industrial countries are now convinced this is the way to go. And what we're doing here is helping them, actually. I mean, with you, the younger generation, we are helping to shape the world for you, okay? It's important because you are the ones who are going to pay for the mistakes that were done in the past, and you're the ones, unfortunately, who need to work to repair this world. Okay, so when we're looking at hydrogen, there are three main forms of hydrogen. There's a wider spectrum, but I like to look at three different distinct types of hydrogen. Gray hydrogen. Gray hydrogen is produced from natural gas, and in the process, it releases CO2. We do not want to see that CO2 being released. And so, but gray hydrogen is still being used quite a bit by industry, and we'd like to transition to something that is not polluting. The two options that are not polluting are blue hydrogen. In the case of blue hydrogen, we're taking the CO2 that is emitted in the same process where we make gray hydrogen. We take that CO2 and we bury it or use it for other applications. This is still under research and not very well developed technology yet. And then the technology that is really developed and doesn't pollute at all is the green hydrogen. This is what we'd like to see eventually, that all of the hydrogen that we're going to produce and use will be green. Green hydrogen means that we are using solar panels or windmills in order to produce the energy that we need to break up the water. When we break up the water, we end up with H2, which is hydrogen, and O2, which is oxygen that is going up in the air and doesn't do anything bad to us. Okay, so this is the way to go. So as I explained, basically take the energy harvesting technology, it be solar panels or windmills, do electrolysis, basically break up water, store it, and then use it either to fuel your automobiles or use it for industry, as I explained before. Okay, the prices of hydrogen are becoming cheaper and cheaper as we go. And today it's actually cheaper to fuel your car with, let's say in European countries, it's cheaper to fuel your car with hydrogen than fueling it with gasoline. Okay, so now it makes sense economically. And when it makes sense economically, people are interested in it. And hopefully we'll see more and more interest growing all over the world. Okay, when we look at our region and we look at Israel and the Middle East and Northern Africa, you can see that these countries have an abundance of sunlight and they could use it to produce large quantities of hydrogen, whereas Europe has quite a bit of wind and they could use that to produce their hydrogen. The way, at least how Europe looks at it, is that we are going to produce their hydrogen and ship it to there. We'll see. We're all going to need hydrogen eventually, and each would need to take care of its own. The good news is that we all have the renewable sources. We all have water. Okay, we're all surrounded by the sea. We could use that water to produce that hydrogen. That's not unlike gasoline or oil, which is produced mostly in unstable countries. Here we are reliant on sustainable sources, which we could find all over the world, and water, which is also available all over the world. Okay, so that basically breaks off the ties to those less stable countries, and we can each produce our own energy if we wanted to. Okay, so this is how the Europeans look at it. Basically, what you see here in orange is the lines that are coming from the Middle East and Northern Africa to Northern Europe, and later we'll understand why Northern Europe. And then in blue, you can see the lines that will come out from Northern Europe to the rest of Europe. So basically, we have a sort of a network of arteries and veins, one pumping all the hydrogen towards the north, and then one that is distributing it to whoever needs it. Okay, the reason for all the hydrogen to go to the north is storage. So one of the solutions for storing large quantities of hydrogen is in salt caverns. And apparently we have quite a bit of them in Northern Europe, in Germany, in Poland, a little bit in the Netherlands, and Denmark. And we could use them to store huge quantities of hydrogen that we produce either in Europe or in Africa and Northern Africa and the Middle East. And this is the reason why we see that all of the hydrogen is getting to that region and then spread back in smaller lines to the rest of Europe. Okay, these caverns are basically salt caverns. So basically imagine that we have a block of salt, really dense, that we could, and some holes in it, and we could utilize it to basically hold our hydrogen inside. Okay, this is one of the only geologies that could hold hydrogen in a natural cavern. Other solutions are man-made, so that would be either large cylinders or other solutions that we can discuss later. Okay, so at the heart of the hydrogen economy and hydrogen or electricity produced from hydrogen as a whole lies fuel cells technologies. Fuel cells are a device that converts the chemical energy that is stored in hydrogen directly into electricity. The way this works is we flow hydrogen to an anode. The hydrogen is being oxidized into protons and electrons, and we have a cathode that breathes oxygen from the air and reacts with the hydrogen to give water. this is how it looks like. We'll be flowing hydrogen to the anode. The hydrogen breaks up, the H2 breaks up into H pluses. Okay, so we have two H's, and we break them apart into into the separate components. By doing this, we are getting those electrons, or the electricity that we need. The electrons are conveyed through a conductor to our device that we'd like to operate, and then from there to the cathode. In the cathode, they emit the oxygen plus the protons to give us water. Okay, so basically what we have here is conversion of chemical energy into electricity in a very relatively easy and environmentally friendly process, which produces only water. This is what you're going to see at the exhaust of a fuel cell operated car, drips of water coming out. Okay. Now, I want to take you back to this slide. Sorry for jumping back and forth to this slide. So the biggest advantage of fuel cells over the batteries that we use today in cars is that they have the ability to store quite a bit of energy. If you look at the x-axis here, this is a logarithmic axis, which means that we're jumping in orders of magnitudes here. And what we can see is that fuel cells can hold 10 times more energy than any of the batteries that we use today. Okay, what does it mean? It means that in a car, let's imagine a car that has 100 kilograms of batteries and could drive for 100 kilometers. Okay, if we replace that 100 kilograms of batteries with 100 kilograms of hydrogen and fuel cell, then we'll be able to drive 10 times as much. We'll be able to drive 1,000 kilometers on the same weight. Okay, this is important. This is a game changer for many industries, including the automotive industry. And here is a comparison for you between a Tesla. So this is a Tesla Model S, which the batteries in this car weighs about 600 kilograms, and the range of the car is less than 500 kilometers. Whereas in a fuel cell system, we have 200 kilogram system that with the range of over 1,000 kilometers today in this car. Okay, so we don't carry as much energy, as much weight, and moving weight around consume energy. So we're basically saving on the weight, and we're extending the range of our cars. Okay, in Germany, decided to try and figure out what would make more sense for them economically, and they compared battery charging stations and battery operated cars to the left here versus what it takes to have hydrogen operated infrastructure. So on the battery side, they said, okay, we need to put money into our transmission lines, distribution grid, and then invest in fast and slow chargers to charge our cars. And in the case of hydrogen, we need to put money into electrolyzers to produce hydrogen. We need to transport it, and then we need to have hydrogen pumping stations. And just on the basis of the cost of infrastructure, they came up with the conclusion that it would be $10 billion euros less to invest in hydrogen infrastructure than in a battery infrastructure. And they decided, this is one of the decision makers for Germany and the rest of Europe actually, to go on hydrogen. Okay, so another point that helped convince both the EU and also customers is the charging time. And what we could see here in the figure is how long does it take to charge a battery operated car versus fuel hydrogen in a car. As we could see here, it's 15 times faster to refuel a car with hydrogen than charge it with a fast charger. Okay, so that means that instead of waiting in the station for about let's say 40-50 minutes to charge your Tesla, if you come with your car and you just fill it up with hydrogen, it's going to take you about 3 minutes. Okay, that's another game changer, because none of us wants to stop at the gasoline station for more than those 3 to 4 minutes. None of us want to stay there for about 40 minutes or 50 minutes to charge their car. Okay, so this is another thing that may convince customers to use more and more hydrogen in their cars. As we see, and as I mentioned at the beginning, we see lots of applications coming up. Anything from server farms. So what you see here to the top left, you basically see fuel cells that are operated with hydrogen and produce energy for server farms that are being used by Apple, Google, and Amazon and other companies. You can see next to it the Toyota Mirai. Now there's a new version, even nicer looking version of the Toyota Mirai. Still staying at the top, we can see drones. So this drone here is a drone that we developed here in the lab, and it's flying in the air. This drone stays up in the air 4 times longer compared to the same drone. It's operated by batteries, same weight. This drone weighs about 23 kilograms. We see submarines using hydrogen to propel themselves. Trains today in Europe, we have about 20 trains that are operating on hydrogen. We have hydrogen storage and use in houses and businesses, trucks, and so on. So we start having lots of interesting applications, and as time goes by, I would expect to see even more applications coming up. Okay, this is a picture from a couple of summers ago. I was in California with a friend. I was in charge of this hydrogen filling station. Came to visit. There's only one hydrogen filling station in that area, and what you can see here is a line of cars waiting for this just one station. We'd like to have more stations. I'm not waiting in line because it takes too long, again, 3 to 4 minutes to fill up the car. But basically, there was just one station at a time. Now they built up another one, and this is the reason why you have the line. But you could see those cars in California now driving everywhere. You can park your car, in a supermarket and find a couple of them just next to you, and so on. So it's fun to see those all over Europe, US, the Far East, and soon also in Israel. So in Israel, we already have 3 hydrogen trucks that will be operational starting next month. Okay, with that, I'd like to thank you all for being so quiet and listening, and be happy to take any of your questions. So you could unmute yourself if you wanted to, and I'll be happy to answer the questions. I would appreciate if you could turn on your cameras also. That would be nicer.
Guys, turn on your cameras.
Lior?
Hi.
Lior,
Yes.
I would like to start. First of all, I want to thank you for the presentation. If it's so good, why I'm still charging my car, and all the market speaks about electric cars, and why I'm charging my cars or by electric station or by fuel or by gas? Because I'm listening to you and I'm saying, wow, here is a game changer, but it's not. So what are the obstacles? What are challenges?
Okay, so this is a very good question. The reason why we don't see as many hydrogen cars as we see as battery cars on the road is because of the question of the chicken and the egg. Okay, so what happened is that we need the infrastructure to basically supply the hydrogen for us, but also we need the cars, and the car makers are saying, we are not going to invest in that infrastructure. We're not going to invest in pipelines, in production, in building up those, the capabilities with salt caverns to store hydrogen and so on. We're not going to pay for this. Someone needs to pay for it, and then they are not producing as many cars. So recently we see governments picking up the bill and investing in infrastructure, and we see that ramping up. But it's taking some time. It's taking time because these things are expensive, because it takes some time to build them up. There's a huge demand, and there are only a few companies that are capable of doing this. And believe me, those those companies are backlogged and cannot produce 10th of the demand that they have today. So we will see new players in the market, bigger players in the market that will enable the building up of the infrastructure. We have the funding now, so we solved that. Now the next stage is building out the infrastructure, and once we do that, then we'll see more applications on the road, in industry, and so on. But there are still challenges. So there are still challenges, the biggest of which is large energy storage. So as I mentioned before, in Europe, they sort of have a solution for this. So they decided that they're gonna basically store large quantities of hydrogen underground in those salt caverns. But this is, area-specific solution. So for instance, in Israel, we don't have that solution. So we need to figure out a way to store large quantities of hydrogen. And that's holding us back, actually. Okay, so this is one hurdle that we need to figure out how to overcome. Another problem is in arid places where you don't have as much water or do not have access to water, and then they'll need to figure out how do they make hydrogen, because we make hydrogen from water. So this is another issue that needs to be solved. And there are also scientific issues, and we would like to have more durable, more efficient technologies. We're working on this as well.
Thank you, Lior. Guys, the stage is yours, so feel free to ask any questions you want to. So if you started working on your project, I know some of you have already had questions that you asked your mentors. Eleonora, you have a question? Okay.
So hi, everybody. I will not be able to talk for a lot of time. I wanted to thank everybody for being here. And while I don't have a personal question, I would like all the groups to think of at least one important question for their project and ask it now, because now is a good time. Ask.
So for example, Noah, I know you had a question, yeah?
Me?
Yeah, no?
I didn't ask anything.
Okay.
So
Anyone?
let me ask you a question. So raise your hand if you've seen any application that uses hydrogen.
Any what?
No one is any application that uses hydrogen. Have you seen a hydrogen propelled car, truck? Have you seen a hydrogen filling station? No? Wow. Okay, so we need to take care of that.
So I'd like to ask a question. Are there any alternatives to storing hydrogen as a gas and compressing it down and cooling it to what, 20 Kelvin or 77 Kelvin? So is there any way we could store this in other chemical carriers at room temperature? Are there any potential materials that could be used for this?
Yes, so there are many companies, small startup companies that are trying to develop hydrogen carriers that could be in solid state, so metals that form metal hydrides, and basically imagine a sort of a marble that basically clings hydrogen to it. So these are metal hydrides. Others are trying to make liquid hydrogen carriers of all different sorts. One of the most popular ones is ammonia. Ammonia is NH3, and basically anything with an H on it could be used as a sort of hydrogen carrier. The magic number there is 5.5. 5.5 is the weight percent of hydrogen in a cylinder. So imagine a cylinder that weighs about 100 kilograms with 5 kilograms of hydrogen or 5.5 kilograms of hydrogen in it. This is what you need to beat in order to make a compelling case of using your technology as a hydrogen carrier. Okay, so if you have a metal hydride, it needs to have more than 5.5 weight percent of hydrogen on it. If you have a liquid hydrogen carrier, it has to have the same. Okay, and then comes safety, and then comes energy and cost. Okay, so you need to take all of these parameters into one equation, bring them into one equation, and try to solve it in order to make, again, a compelling case of using alternatives. Again, there are various companies who are offering alternatives. I'm sure that some are good and will make it to the market eventually.
And thank you. So, for example, using ammonia or other liquid carriers, is that more? Does that count as more? How would you say that? Does liquid or organic carriers for hydrogen have more potential than, for example, metal halides and maybe metal organic frameworks and such?
Yeah. So again, if we go by the number, so if you can calculate, the weight of, what's the weight of ammonia, the molecular weight,
17. That's 3 17s.
So we have 3 hydrogens on it. So that's 3 divided by 17. So that's more than 5.5. So we could check mark that. We could tick that box and say, okay, weight percent, we already have it. Okay, but ammonia is a hazardous material. It is poisonous, and that brings up certain complications. In addition, we need to make ammonia, and this is an energy-intensive process. Okay, so we pay some penalty by putting hydrogen instead of compressing it. Even when you compress it, you pay a penalty. But we need to compare those penalties in energy and say which would be cheaper. Did I answer that question, or did you mean something else?
Yes, I guess.
I have another question. So on your PowerPoint, we could see that Europe will be utilizing pipelines, but are pipelines the best, or are like ships carrying liquefied hydrogen gas also an option?
So in between countries, we will need to start with ships to transport hydrogen. But later on, I think investment, it's going to be a huge investment. But investing in a pipeline would make more sense to transport hydrogen. Just like what we, one of the biggest pipelines in the world is the pipeline between Russia and Europe that unfortunately, giving us some trouble lately. But this pipeline is transporting natural gas from Russia to Europe. Okay, there are ways to transport it in ships and on trucks, but the cheapest way to do it, and actually the easiest way to do it, is in pipelines. It will require an investment, but eventually it will pay off. So even for instance, we are looking at the option of transporting hydrogen from Israel or from the Middle East to Europe. At the beginning, we will need to transport it using ships, either in liquefied form or using hydrogen carriers. But eventually, we would like to see a pipeline that basically will help us transport it.
Thank you.
May I have a question? If there is a hydrogen pipeline, wouldn't it be like very, very, very dangerous wise if there is a small fire in one end of it, wouldn't it reach the other end? Like,
so this goes back to the safety issue. Engineering wise, we know how to deal with those fires. Now, if we could turn off a valve, those systems would have many valves along the way, and if there is a fire somewhere in the middle, we just cut it off by turning off the valves and stopping the supply of hydrogen, and that we're killing the fire. Okay, this is the very same problem that you would have with natural gas as well. there was a James Bond movie, or maybe a few, just on that, on terrorists trying to attack a natural gas line and trying to blow it up, and there are ways to deal with it. Okay, but the fact is that this is how we do business today. We're transporting most of our energy in pipelines, and we know how to handle it. Hydrogen would not be any different risk than the rest of them. And as I mentioned, actually, much lower risks than the rest of them.
Thank you.
I'm not hearing the girls.
Ladies.
I don't have a question in mind, but if I do, can you give us your email maybe?
Yeah, I'm sure Nama could share some contact.
It's a good point.
Okay, I have a question. So I'm in the group that is trying to substitute the fuel for ship or plane engines. And so now we are having a little bit of a doubt whether we want to use either fuel cells or the internal combustion engines, because the main difference is that the internal combustion engines are much easier to implement because only a few parts need to be swapped. The fuel leads to the engine, and it will be much easier to implement in the current vehicles. And considering that the average ship age, for example, is about 27 years, it would mean that the hydrogen technology would take about 20 to 30 years to even have an effect on anything that we've done. And the main reason not to use the internal combustion engines is because they still leave some dangerous gases that can cause problems, but it's, as much as I can see, it's at a much smaller level than the regular diesel or gas engines. So do you have a suggestion on that?
Yeah, that's also a very interesting question. So I'd like you talked about ships, but I would like you to go to the air and talk about aviation. So for aviation, electricity is not a good solution because if we would use propellers in airplanes, then we limit the speed significantly, and we like to use the jet engines that we see in most airplanes. And in order to do that, you need to burn fuel. Okay. Now the solution that hydrogen brings us to burning fuel is there are two solutions. One, we could burn hydrogen, and today, and just recently, Rolls-Royce, which is a major producer of jet engines, said that they managed to make jets jet engines that operate on pure hydrogen. But this is not the solution that you were looking for. You were looking for a solution that uses the same engines that we use today. And to that, we have what we call sustainable aviation fuels. What is a sustainable aviation fuel? Sustainable aviation fuel, we take CO2 from the atmosphere, we produce hydrogen, we combine the two and make CO and hydrogen. CO and hydrogen are precursors to make that sustainable aviation fuel through a process called Fischer-Tropsch, a process that combines carbon and hydrogen to build short chains of carbonaceous fuel, and that could be used in airplanes today. So basically, what I'm saying is, if we are producing hydrogen, we could use basically a net zero scheme where we use those sustainable aviation fuels to operate airplanes without changing anything in the airplane itself. Okay, so we're producing synthetic fuels using green hydrogen. Does that convince you a little bit?
Yes, thank you very much.
But look up on the web, look up SAF, Sustainable Aviation Fuel.
Guys, anyone else has a question at the moment?
Just a general question.
Yeah. Yes, Pia.
Because all of us are currently researching on hydrogen, and I would just like to ask you if you have any recommendations where to start when we are informing us about hydrogen. Maybe you have some useful tips for us.
So I need you to be a bit more specific, because as you saw, there is the production, there is the storage, there is the different usage. Let me know which one is more interesting to you, and we could talk about that.
So in my case, it would be the storage that is especially interesting.
Okay, so storage, I think storage would be very interesting. And we discussed this a bit before. I would try to focus on liquid hydrogen carriers, all sorts of liquid hydrogen carriers. That may be, as we mentioned, ammonia, but there could be also methanol is a sort of a liquid hydrogen carrier, and other organic materials could be used to carry hydrogen. So it would be nice to start looking at those options and use those thumb rules that I mentioned before, which is how much hydrogen can we carry on each molecule, okay? How easily can we release it from that molecule? Is it an energy intensive process or not, if we can release it quickly or not? And how safe are these materials, okay? So try to look at those three parameters when you look at different liquid hydrogen carriers.
Thank you.
Welcome.
So if before we end, I want to first of all thank you, Lior, for sharing your knowledge and taking the time to talk to us. If you are thinking of any other questions that might come up over the next couple of days, then email them to Eleonora or to me, and we will email it to Lior and see maybe he's able to answer. But along the way, and also during the competition, once you're in Israel, we have more mentors who will be able to help you with all these questions that might come up, that will, okay? Cool, set.
Okay. So I'm really happy to see so many faces that are new to me in the hydrogen domain. And I told you, I mean, we rely on you. Unfortunately, not my generation, actually the generation before me, made these problems. But your generation is the generation that will probably solve them. And you need to start working hard now.
So thank you so much, Lior. Guys, Eleonora, you want to say something to everyone before we say adios? Maybe repeat what you said in the beginning.
Yes, so as I was saying, please guys, just take a look at your email. I will be waiting for an answer in a few days maximum, please. And for all other stuff like sources and researches, and even if you are having some problems with your calculations, don't be scared. Write me, we can call, we can chat. I'm super easy to talk to, and so don't be scared, just ask, okay? It was a pleasure. Thank you very much, Lior. Bye. Thank you.
So thank you, guys. Good luck with the rest of the competition. We will see you soon. We're going to have another Zoom. We haven't told everyone yet, but we will announce it during the next couple of days. Okay? So,
Goodbye.
ciao.